Hello and welcome. In this video we're going to implement a command system for our game. Previously we were handling actions like mouse clicks in a simple way, telling our game state to change directly. With a command system, actions are treated like objects. We build the command, pass it to the game state, and it handles it. The benefit of this is, since actions are objects, the game state can stack up a whole bunch of history, which is easy to undo. I once dated a girl who'd undo moves when we played chess. Not the best idea from a gameplay point of view, but for programming, it's a neat trick. This video follows along from our previous session on constructors. You can find both a start point and finished code in the GitHub in the video description below. With that out of the way, I hope you enjoy the video. This is a great example of applying an elegant and useful design pattern in Rust, and will come in handy if you want to create a level editing tool, for instance. Anyway, let's get started. When I'm trying to solve a programming problem, I try to break it down into subproblems. As far as I can see, there are 3 tasks. Task A, make a growable and shrinkable array. Task B, make an object representing a piece drop command with both a do and undo action. Task C, bring it all together. Give the game state a list of commands, pass commands to it from the main function, and give it functions to undo and redo its history. Okay, let's get to task A. Okay, so luckily Rust gives us a vec class, which we can use. A vector is a growable and shrinkable array, which is just what we need. So let's go ahead, make one, and play around with it. Okay, so I've made a vector, and I pushed some things onto it. It's not happy with that, but I can fix that up by making it a mutable vector, so we can modify it. So we can get a bunch of parameters for the vector. Okay, so we have length and capacity. Length is the number of things which are currently on the vector, and capacity is the amount of space which is reserved for elements. Okay, we can run this right now. And we see down below that we have 2 elements, just like we pushed on here. We actually have space reserved for 4 elements. So this may come from, it doesn't matter where it comes from. We always have to have more capacity than what we have allocated in most cases. I believe it comes from the doubling strategy. So first of all, we make a vector with no size and we push something on, a resize occurs. Every time a resize occurs, it's statistically optimal to double the size each time. But we don't have to worry about this at all. Let's go ahead and print out everything which is in that vector. Okay, excellent. So we can look at that. Doesn't quite seem to work. Let's try that again. There we go. Okay. Excellent. So there we've got it. Cool. So the next thing we want to do is take something away from our vector. So we'll just grab all of this code and run this, and instead of pushing things on, I will simply pop it off. So pop off one element and rerun the whole routine. Okay, let's try that again. Alrighty, so have a look at this. The first time we put on 2 elements, there they are. Then we called pop, and now we have 1 element left. We still have a capacity of 4, that's totally fine. We can read this off and say, yes, we have in fact removed 1 element. Perfect. Note that pop removes from the back. We also have a remove function, so we could say something like v remove, and then we take the index of the position we want to remove, but for this video we're just going to use pop. We're just going to pop from the back. Okay, so we've put on 2 elements, we've popped off 1 element. What if we want to put on a whole bunch of elements and then resize the vector? So let's go, we've got a size of 1, so this will be, what am I thinking? 3, 5, 7, I believe. We can confirm that. Okay, run that. Yeah, that's right, we do have 7 elements. Okay, so what if I just want to keep 4 elements? I'm going to repeatedly call pop. So if I want to keep the first 4 elements, 0, 1, 2, 3, okay, well I have 7 elements. 7 minus 4 is 3, so I want to pop off 3 times. So I'll just go in here and we'll say okay, so size minus 4, 7 minus 4 is 3, and then I'll just loop through. So I'll say for something in and then I'll just grab the state again. Okay, cool. So again, at this point we have 7 elements in our vector. I want to pop off all but the first 4, so I calculate how many times I'm going to have to call pop, and then I run it, and let's see if that worked. Alrighty, yeah, so we have 4 elements, and there they are. We can confirm that that is working correctly. This will be useful when we're working on our commands, because if I've undone a whole bunch of commands and then I drop a piece, I want to flush off my history from that point onwards. So there we go. So there we have it. All these vector operations are just demos at the moment, but later on we'll use all of these operations to manage our game's history. Okay, so on to task B. Task B is to implement a command object, which can be done, it can be undone, and all of that. So I'll just close all of this down and make some space, and I'm going to put my command object right at the bottom here. Okay, so I'm just going to go okay, so this command represents the act of dropping a piece down on the board. In order to do that, we simply need to know which row and column we're dropping it and which piece we're dropping. Now let's have a look at the functions which will be implemented for that struct. Okay, so at this point I'm going to have 3 functions. Okay, those 3 functions are, we need to do the action. In order to do this, we're also going to take not only ourselves, but borrow a mutable reference to a game state object so that we can modify that game state. And similarly, same for undo. And then we need to handle the case of, like, what do we do if we've got a command which is invalid? Easiest thing to do is to actually, well, we're not going to modify the game state. We'll just read the game state, check what our move is, and it should be pretty easy to check whether it's actually a valid move or not. So let's perform the move first. So in order to perform the move, first of all, we'll tell the game that, let's just take a second. Okay, we'll tell the game that the player, which is dropping the piece in the command, we'll tell them that it's dropped a piece. So we'll increase its number of pieces dropped for that player. Then secondly, we'll get the game board and we'll set the corresponding entry to our piece. Then the next thing we'll have to do is we will have to swap the current player. So we'll say if the command's player is red, then now the current player will be the black piece. Otherwise, the current player will be the red piece. We're really just setting it to the opposite of the player that just dropped the piece in the command object. Okay, cool. Now to undo the command. So to undo the command, we will pretty much do the opposite. So for the current piece associated with this command, well, it's just picked up a piece off the board. So we'll reduce that count by 1. And then the spot on the board, we can reset it to none. And then finally, well, the piece which just was undone, in other words, the piece which just picked itself up off the board, will now have to be the current player because it'll be, well, it's undone its move. It's going to go again. Okay, so look at how neat that is. We have an option, or you have a command which has its arguments ready to go. We know how to perform it. We know how to undo it. We then just need to check if the command is valid. And for this, we're going to use all of the checks from before. So if we go back to the game state, we can look at all of these. We should only be performing a command if its row and column are in range, if the player that is going to drop the piece has pieces to drop, and if the spot that we're dropping on is empty. So we'll take that check and perform it down here. So this function also should return a boolean to indicate true or false. So there we have it. All we're doing, this is not a mutable reference, we're just reading the state that's in the board right now. We're just doing these checks in range with a player that can drop pieces on a spot that is empty. Okay, so really that's it. We can close this down and let's make a function to test our, to test our commands. So I'll just pop over here. Oh, another thing. Let me go here to the game, and we can actually include a whole bunch of these as one statement. Just have to make that a public struct. It's not going to be public in the final, but just for this test. There we go. Okay, cool. Okay, so for this test, I'm going to make two commands. One is just to drop red on row 0, column 1, and the second one is to drop black on that same position. Okay, no worries. So I'll just go down to just after we've made the game state, and I'll just run that test function. Okay, and we'll go command 1 perform on the game. Okay, so as you can see, command 1, the red piece has been dropped. Now if I go to click again, I'm onto the black player, so the command has worked properly. So what I can do now is just check whether the second move would be valid now that I've dropped that red piece. Alrighty, so have a look at there. We've got that the second drop is not valid because it's going to fall on that same piece. So no problem. What we can do is go command 1, undo, and then try that again. Alright, so that command has been undone and the black drop is going to be valid, so then we can go perform command 2. Excellent. Perfect. Cool, so I'm pretty happy with the commands. I think that's working well. Can leave that for now. Okay, so now let's give our game some history. Let's do it. So I'll just close this down. That's fine for now. And we'll just go back to the game state. And I'm going to give this struct a few fields. First of all, I'm going to have a variable called history, and that will be a vector of commands. And then finally, I just want to keep track of the current position within the history. So imagine that a history is a whole list of commands which have been performed. History position is an integer, basically, that points to the current command that we're on. So we can undo, and that will step us back through our history. We can redo, and that will step us forward through our history. Okay, so we'll just go to the constructor, and we're going to need a few extra bits. So I'm going to need to set the history and the history position, which I guess we'll start that at 0. There we go. Excellent, so that's the constructor. These functions, I could get rid of them, but why? Why not? Okay, so handle click. So I know I said before that I would pass this from the main function, but that is a little clunky. So what I'll do is I'll leave that as public struct, who cares? But I will handle this within the handle click function. So when we go and get a click command, get a click message, we want to make a command. So we'll go make a command. Okay, great. So we're just baking in the row and column of the mouse click and the current player according to the game. All right, so next thing I want to do is check if the command is valid or not. Easiest thing to do to avoid massive nesting is just pretty much exit if it's not valid. Okay, so if it's not valid, yeah, we had to go. Let's leave now. Now the next thing I want to do is every time I click, I want to clear off my history. I want to clear off my history from this point onwards. So I'll say so again, think about this. This is just like the example I did before. The number of elements I want to keep is my current history position plus 1. Say, for instance, I've got 5 things in my history chain, and currently I'm on position number 1, well then I want to clear off all but 2 elements. Okay, so 5 minus 2 is 3. Fingers crossed, hopefully this works. And then I'll loop through. So I'll go, by the way, this underscore is just indicating that I'm not using the numeric value of the loop. Okay, so we pop off everything that we need to. And then I'll be very careful here. I'll get to this in a second, but for now I'll just do it this way. So I'll say command perform. So I perform the command first, and then I push it onto the history. Now when I drop down a piece, I'm always flushing my history, so I always know that the last thing I've got on my history vector is the position that I should be working from. So, okay, I'll step through that again because it's quite a bit. So again, I make a new command to drop down at this current row and position. I check if it's valid or not, early exit if it's not. I clear off everything beyond the current position because dropping a piece will flush my history from the current point forwards. Then I perform the command and push it onto my history. Okay, we can get rid of this next turn function that's already being handled by the commands. I've got 2 more. That is to redo an action and to undo an action. First of all, I'll just check if I'm at the end of my history, basically, if I've got actually nothing to redo. But otherwise, what I'll do is I will step my position forwards by 1, and then perform whatever action is there. So this is where things are going to get a little bit funky. So I'll go, okay, get my history, access it based on my history position. Okay, so far so good. Ooh, maybe so far not so good. And then I will perform that. And what I want to do is pass in self. But it doesn't like that. And it goes funky. It says cannot borrow, what does it say here? Cannot borrow self as mutable because it's also borrowed as immutable. That's weird, right? So in this case, I would do what I call the rust shuffle. You know what I mean, the rust shuffle, where I look through all this stuff and I change all the references around and I make a mutable thing, a reference to a mutable reference to a mutable thing, and put myself through a lot of agony. But there's an easier way. The first step is to understand why this is even a problem. So it says that we've got all these weird borrows, and it says that all the borrows are happening in line 90. But that doesn't make sense, right? Well, it's a bit funky. Here's how it works. What I'm doing is when I go to perform the action, I borrow myself and throw that in there. But at the same time, I'm borrowing myself in order to access my state. Let me say it like this. I'm accessing my state and then modifying my state based on something that I borrowed from myself. Like, it's weird. It's weird. And it turns out there's a nice solution here. And the solution basically is, if I look at my command doesn't have to be changed. It's read only. So it's simple enough to make a constructor, or rather a copy constructor. So I'll go down here and say, okay, let's make a public function called copy. And I don't even need a mutable reference to myself because I'm just reading. Okay, and what I'll do is I'll construct an instance of a command which just happens to have exactly the same stuff. Alrighty, there we have it. We return that. So I can go back and say, okay, There we go. Okay. So I say, alrighty, look at the current thing in there, grab a copy of it, and then use that. There we have it. Actually very neat. So then I can just copy that, and I'll make the undo. So here the test is basically if we've got nothing to undo. Okay, so yep, so we've got nothing there. And then I'll get the current command and undo it. And then I'll just check, because I don't want to subtract from my position if it's actually already at 0. That'll just cause the program to panic. Okay, cool. So as it turns out, you may notice here, if we are just on the 0th command, then we will just keep undoing it. But that's perfectly fine, because you can undo the same command as many times as you want, I think. Oh. It's a little dodgy, but let's do it anyway. Actually, it's not that hard to do this. So if we just go to the piece drop command and then go to the undo, we'll just add an extra test there. So the issue with continually undoing a command is it will keep reducing the number of pieces which have been dropped, but we can put a check here and say, well, if the current player has actually dropped no pieces, then just return. I think that's fine. Okay, so excellent. We've got that all set up. We can now go to our main function and just set this up so that we can do and undo commands. So we'll go to the main, and then right down here where we're handling events. Okay, and the only thing we really care about is the scan code. And I'll do U for undo and R for redo. So we'll go there we go. Okay, excellent. So if we see a U, we tell our game state to undo something. If we see an R, we tell it to redo it. So let's go ahead and test this. Just run that now. Okay, so I'm in the game. I just hit U to undo. Nothing happens and no errors. R to redo. Let's drop a piece and undo that and redo it. Okay, that's interesting. Okay, so after about a metric hour of debugging, I found the error. It's always something trivial. What I had is, I think I had something like row and row here in the constructor, so it was giving a dodgy copy, but now that should be working. Let's give it a go. Let's try it out. So I can go click, undo, read. Oh, come on. Okay, let's try this. Undo, redo, undo, redo. Okay, excellent. Drop down a few of these. Okay, now let's try undoing. 1, 2, 3. And now I'll pop it somewhere else. So I've flushed my history. If I go redo, nothing. I can still undo, but that has flushed my history. Okay, we go undo. It should be the red player's turn again. Okay, cool. So there we have it. Didn't take long. And that's it. We're now implementing the command design pattern in Rust. Hopefully you can see the elegance and power of this, and maybe you can come up with some uses for it in your own projects. If you found this tutorial helpful, please consider supporting the channel on Patreon. It's $2.50 a month for video credit, and it really helps keep the channel open so everyone can learn and benefit. Anyway, all the best, and I'll see you again next time. Bye!